ABC. I want to talk to you about the definite integral today. We've already had this sort of definition that the definite integral for a curve above the x-axis, those are all the ones that we looked at, was the area underneath the curve, right? So we had these examples previously. So old example over here. Old example, we had something like, x squared plus 1 or something. We said x squared plus 1, and that looks something like this, right? Looks something like this. And we said, we could find the area on the interval from 1 to 3, for instance. If we wanted to find this area, this shaded area in here, right? Well, that was equal to the integral. So area is equal to the integral from 1 to 3 of x squared plus 1 dx. Remember, we'd integrate that, and we'd say, we'd take the antiderivative, and that would be 1/3 x cubed plus x, and then we sort of evaluated at 1 and 3. Remember, we had to take the difference, right? We took the value at 3, minus the value at 1. Minus value at 1. Be careful that we distribute this negative sign properly. Okay, so we said that was true for any curve that was always positive, right? Anything that was above the x-axis. We didn't really have anything below the x-axis until today. Okay, so on that handout I gave you after your test, I'll try to remember to post it to Canvas also. Right, we have this curve that looks something like the thing I've drawn up here. My drawing's kind of bad, but we have something that looks like this, right? And we have these areas, and I shaded the ones above the x-axis, with green, and the ones below the x-axis with y, because there's sort of two ways we could add up this area. If I were to ask you to add up the area under the curve between -6 and 7, right? There's sort of two things it could be. It could either be 5 plus 7 plus 3, and we just add up the area. We don't care if it's positive or negative. Or it could be 7 minus 5 minus 3, right? Because that red area is negative. And it turns out that is actually what we're going to use. So we're going to have this notion of net signed area, where if it's above the x-axis, it's positive, and if it's below the x-axis, it's negative. Okay? So the first three examples are fairly straightforward, right? If I want to take the integral from -2 to 3 of f of x, right? This function is my f of x, right? If I want to take this integral from -2 to 3 of f of x dx, well, I don't know what f is, right? So I can't possibly integrate it, right? I can't know what its antiderivative is. So instead, I have to rely on this area method. Remember, if this was like some sort of triangle, this guy over here, some sort of triangle, we could just calculate the area. We wouldn't have to do any calculus. So here we're given the area. That's 7, right? So this thing is just 7, because this says, hey, the area under f of x between -2 and 3 is 7, right? That's sort of a given. It's circled on your paper, okay? So let's talk about the next thing, right? What if I had the integral from -6 to -2 of f of x dx? Well, this is all below the curve, right? We're talking about this region in here. It's below the x-axis. And so that area actually counts as negative. So instead of saying this area is 5, right, we say this area, because again, we're concerned about net signed area, right? We care about the sign of these things. We care about whether they're below or above the x-axis. This is actually just -5. -5. Okay. I'll let you work out why 3 is -1, but I'm not going to spend some time doing that. I want to talk about the next sort of set of rules, right? So again, we're concerned about area above the x-axis minus area below the x-axis, right? So our rule is going to be our area equals area above the x-axis minus area below, right? That's sort of the big thing that we take away from here. Okay, so let's talk about these 5 rules. And for these guys, I'm going to draw draw some random curve here, and all of these rules are going to apply for functions that are above or below the x-axis. It's just sort of easier for me to talk about one that's always positive, right? It's easier visually. So let's say I have this function, and I'm concerned about this region here from A to B. Okay? And we're going to have a lot of rules here. So the first rule here on your sheet on the bottom of page 1, right, is saying, what if I take this integral from A to A? So that meant, right, what if I have this integral and I want to know the area under the curve between A and A? Well, that thing has 0 width, right? So that thing is always, of course, going to be 0. And if we were to use our definition up above, right, where I had some, right, if we were to say if f, big F of x is the antiderivative, an antiderivative, my bad, derivative of f, little f of x, right, then we would get, right, that the integral from a to a of f of x dx would equal big F of A minus big F of A. And of course that's 0, right? That's exactly what we did up here with my 3 and my 1, right? I took F of 3 minus F of 1, right, where F was the integral, big F. So this is sort of rule number 1, right? That if my lower limit, my upper limit are the same, I'm going to have 0. Okay. The next one's a little tricky to think about, okay? And that's if I have A to B, f of x dx. This is actually going to equal negative if I switch the limits. And you might be thinking to yourself, well, that's ridiculous. Why would we ever switch the limits here? Why would I have b over b at the bottom and a at the top? B is to the right of a, right? That doesn't make any sense. So we'd be looking at the area from something, right? You wouldn't say, let me consider the area between 7 and 3. We'd say between 3 and 7. Well, the reason why it's negative, remember when we had that class where we summed up all of these little rectangles, right? We summed up all of these little rectangles in here, and they all had some height, and they all had some delta x as their width. And remember we said if we have n rectangles, delta x was the difference b minus a over n, right? Because it was saying, oh, if I have n rectangles and b minus a is 4 or something, then I'd have 4 over n rectangles. Or each rectangle would be of width 4 over n, right? We'd have n rectangles of width 4 over n. Okay, so it turns out, right, if I just switch these limits, I still get the same heights here, but in, so this is normal here. And then in Weirdland, in Weirdland, maybe we'll use a weird color for that. I don't know, orange, that's a weird color. With limits reversed, my delta x is now a minus b over n, right? Which, and this thing is negative, right? This thing is negative. So we'd still have the same heights, but we'd have these negative things, so we'd actually get a negative area under the curve. Okay, so again, if we switch the limits, we can make it negative, and this is a tool that may help us later on. Okay, that one's sort of the least straightforward of these things, I think. So don't know why we put it second, but there it is. And we should be happy about that. Rule number 3 is exactly what you think it would be, right? If I have the integral of some f of x plus or minus some other function g of x dx. Well, that could just be rewritten as the area under f of x dx plus the area under g of x dx. And why does that make sense? Let's draw 2 curves to sort of illustrate 3. So here's my illustration for 3. If I have some curve here that's, maybe this guy, that'll be f, and then g, maybe g looks like this. Okay, well, at each spot, and then again we're between some a and some b. At each spot I could add up the area, right? Or I could add up the value of the function if I want to find f plus g. F plus g would look something like, I don't know, it would be, maybe it would come down a little bit and then we go back up. I don't know, maybe this is f plus g, right? And I would take the value here plus the value here and then get this thing, right? This would be the sum of these two guys, right? The value here plus the value here would give me this thing up here. Okay, so that's what f plus g would look like. And it doesn't take much convincing to realize that the area under f plus the area under g would be the area under my f plus g, right? If we think about my little rectangles, right, I'd have a little rectangle, maybe here. And I have another little rectangle sort of on top of that, right? And the sum of those areas would equal this third rectangle that went, sort of above both of them, right? Those rectangles added together would sort of equal this guy. You can envision the green guy sort of being put up here, and then they would be the same, right? If we sort of move the green guy on top of the blue guy and stack them. I should add, right, sorry, there's a plus or minus here. This we can subtract also, right? That's fairly obvious. Okay, so that's rule number 3. Rule number 4, right, that's saying that if I'm going from a to c now of some f of x dx, well, that's going to be equal to the sum of two different integrals. The first one we could go to some intermediate point b, and the second one we could go from b to c. And again, the illustration for that one is fairly intuitive, right? Again, I have some random curve up here. I seem to always draw a shape that looks kind of like pi. And then now we have a third point, right? We have this c out here and then some b in between. Well, of course, the area from a to c is going to be equal to the area from a to b plus b to c, right? That's just sort of a fundamental idea from, geometry that we can just sort of see, right? The area from a to c is going to be equal to the area from a to b plus b to c. So that one shouldn't be all that earth-shattering, right? And then the last one, I'm not going to have an illustration for this, right? Because this is just like the sum rule that we just saw. If I have some function k out there, right, I can always just take this and not function k, sorry, constant k, function f. I can just take the constant k and put it out. Okay, so these are sort of the 5 rules that we're going to need to use to manipulate these things. Okay, so I want you now to consider doing 4, 5, and 6 on your own on the second page. Okay, do those. You can pause me. You can let me run. I don't care. And you should sort of be able to get those guys. Okay, okay, so the next thing we want to talk about, right, is that there's sort of 2 ways to think about these area problems. If I'm asked to calculate the area under a function, I could either think about it with purely area, like we're given something, like this example way up here where we were given something, or I could use calculus like I did on the right. So sometimes our functions are going to be fairly simple. So I want to think about an example. I want to think about a different example, not one on your sheet, and then sort of let you guys try to do pages 3 and 4 together tomorrow, maybe with some other practice. Haven't decided yet. Let's say I had some f of x, and let's say that was, x plus 1. X plus 1. It's a very, very simple function. Okay, we can draw it, of course. Here it is, right? X plus 1's got an intercept here, and it sort of goes like this. Sort of like this, okay. And let's suppose I want to find the area under f, between -1 and 4. Okay, well, that's just this region. But we'll use green. -1 to 4. That's just this region, right? That's obviously this region. And there are 2 ways we could get the same answer, right? There's the geometry way and the calculus way. And I know we're so eager to use our calculus knowledge here, but we're actually going to use geometry more often than not today, okay? But we can always use calculus to check ourselves if the function has an antiderivative that we know. So the geometry way and the calculus way. Okay, the geometry way, right, is simply saying, oh, look, that's a triangle. I know that's a triangle. It's got base equal to 5, and it's got height. Height, we have to be careful here, right? This is 4, so f of 4 up here is 5, right? So height of 5 also. So the area must be 1/2 base times height, or 1/2 of 5 squared, so 25 halves. And that's perfectly valid. And for some functions, you might only be able to calculate the area using sort of some geometric structure that you already know. You might not even be able to take the integral. I know that sounds crazy, but stay tuned for class tomorrow. You'll have one. You have one on this sheet even. I'm curious to see if any of you can get that. The calculus method, right, is simple, right? That's just saying from -1 to 4, -1 to 4 of my function x plus 1 dx. And you might say, how on earth are we going to get 25 halves in there? Well, it's going to come, it's going to be kind of cool, right? So we're going to take the antiderivative of x plus 1, which is, of course, 1/2 x squared plus x, and we're going to evaluate that at -1 and 4. And what that means, again, is that we take the f of 4, f being the antiderivative, minus f of -1, which is f of 4 is 1/2 4 squared plus 4 minus 1/2 -1 squared plus -1. So what is this thing over here? This is just 8 plus 4. 8 plus 4. And then this subtraction here is going to be minus -1 squared is just 1, so there's a half plus -1 minus 1. So that's 12 minus -1/2, or 12 plus 1/2, which is, of course, 25 over 2. So we got the same answer going both ways, okay? So tomorrow in class, or today in class, depending on when you watch me, you're going to have functions on pages 3 and 4 of this thing. And I encourage you to sketch and try to solve them either with geometry or with calculus. And when you can, do both. These piecewise guys are going to be tough for us to do with calculus right now, so I would just do those with geometry. But some of the functions on the back page here, I encourage you to try to use calculus and geometry, right? Sort of have both arguments and make sure that they both make sense to you. All right. I'll have some more practice for you tomorrow. And please try to bring these sheets so that you can do 3 and 4 together. Yep.